So I do apologize. I had failed to publish the second week. It's published now, so you can go on to Canvas and download the lecture slides for today. I thought they were published. I missed pushing that little button. I'll try to make sure that doesn't happen again. But good news is we're going to have Wednesday's lecture virtual, but then this Friday is going to be live. So we're gonna go live this Friday. So write that down. I will see you guys in the, I think it's building 20, the EE building, and we will have class live starting on Friday. And I know it's gonna be much better than online. There's just, some things are just difficult to replicate here. So let's go ahead and get started. We'll probably go through all of lecture 4, and then I'll start with lecture 5, and then we'll go through lecture 5, obviously on Wednesday, and then we'll meet live Friday, and then we'll start working on chapter 12. Okay, so in this lecture, what I'd like to do is finish curvilinear motion, and I wonder, did I misspell that? Sure looks like it. I wonder if that's a typo. Anyway, I don't, maybe not, but, and then relative motion. So we'll finish those today. So I want to do an example with projectile motion, including relative motion. Relative motion is going to be a theme that's going to come back again and again throughout the quarter. So we want to try to familiarize ourselves with it. It's easy now because we're sticking to 2D. I don't know if we're going to go 3D relative motion or not, possibly, but we'll see when we get there. The good thing is that the relative motion we're doing now, we can use triangles for, and that's just one other way to solve the problems. It makes it can be easier depending on your method. Now, remember that when we're dealing with relative motion, we always use the equation set up like this, where we know that if we say R of B, the distance of B is equal to RA plus RB relative to A. And so again, an easy way to remember this is just the B and the A go B then A on the other side of the curve, or the equation. You can also write the equation as RB relative to A minus, or I'm sorry, equals R of B minus R of A. And so then it would be B minus A. So you should be able to remember that just by the order of which the letters go. And remember that if you reverse the letters, if you, like, say, for example, you have RB relative to A and it equals 2 vectors, then if you subtract, if you reverse it and make it RA relative to B, then you just reverse the signs on those vectors. And you'll need to do that in the last homework problem. So here's this drawing here on the right side shows you how when you're adding A and B relative to A, it's just like adding vectors, just like we did back in the beginning of statics. You go tip to tail and then you draw that. So, and then you can just add them with components. So there's nothing new that you haven't seen before. Okay. So when we think of relative motion, we think of it as a situation where the boat, in this case, I like this example because what it does is it lets you see how a perspective would be if you were on the helicopter. So if you're sitting on the helicopter and as you're landing, your helicopter view is really just like you're going straight down, because both the ship and the helicopter have a forward motion. So if it's going forward at 5 meters per second, then both of them are moving in the same X direction. And so from their reference frame, it's just like you're moving up and down. So it's similar to if you're on an airplane and you throw a ball in the air, all of you are moving in the same direction. And so the ball just comes straight down again. And so this idea of adding vectors for motion is going to be a common theme that we'll see throughout. Now, in this example, you have 2 cars and you're asked to determine if you're in the car A, then what is the velocity of the car of B relative to A? And so if you're not sure, there's those different arrows that point to which directions they would be. But if you're not sure, just from looking at it, then what you could do is you could just draw it. And so what I mean by that is you can draw your, that you're, actually, let me make sure the screen's showing. There we go. So make sure I get that recorded. Thank you. So you draw your velocity of A, because it's going that way. So there's your velocity A. And also that since you're writing, you want to know that what is the velocity of B relative to A. That that's going to be equal to V of B minus V of A. Or another way to write it is velocity of B equals velocity of B relative to A plus velocity of A. So because you're writing it that way, that if velocity of A is going this way, and that the velocity of B is going that way, then because you have to add this to this, then in order to get from here to that tip, you have to go like that. And so the way I knew where to put the tips and the tails was because I knew that I'm adding B relative to A, and this is V relative to A, this is V relative to B. I'm sorry, this is V of A, this is V of B, this is B relative to A. So I knew that with V of A, I need to add VB relative to A, so I knew I had to go tip to tail on that, and I knew that the two tips converge for VB. And so the answer then is E on this. You want it going like that. So if you're not sure when you look at the problem, draw it graphically and it'll make a lot more sense because the vectors will never be wrong. Just make sure that you understand that this has to be, when you have these have to be tip to tail when you add them. All right. Okay, let's look at another example. Now, let me share this screen again. Okay. All right, so in this example, we have our boat, and we have two boats that leave at the same point on shore. Boat A is traveling 20 feet per second, 30 degrees west of north, and boat B is traveling 15 feet per second at 45 degrees east of north. So what exactly does that mean? So we'll sketch it out, but then, and if you can see my screen, you can see I've kind of already done it. But we want to determine the speed of boat A with respect to boat B. So we're trying to find VA relative to B. And we want to know how long after leaving shore from the same point will the boats be 800 feet apart. So this is what this looks like. We know that both boats left at the same point here. One's going this way, one's going that way. And so we're going to call, this is VA over here, and this is VB over here. Sorry if it's a little blurry. So let's just draw out what VA is. So if we draw out VA, we know that it's just going to equal minus 20. That's its speed. And then that's going to be sine 30. So that's its X component, I. And then plus 20 cosine 30. And that's its J component. All right. Then we want to do, so we end up with essentially minus 10 I plus 17.32 J. And then we do the same thing with B. we get, in that case, it's 15. And for the I, it's going to be cosine 45 plus 15 sine 45. So that's I, and that's J. And so that's the same as, we'll just call that, actually what I usually do is I just write that is 15 times root 2 over 2 for shorthand. I plus 15 root 2 over 2 J. Okay. So we know again that if we want V, question? Okay, sorry. If we know that we have VA relative to B, then we just need to subtract VA minus VB. And so really what we're doing is we're just subtract I components from I components and J from J. And so if we do that, we get minus 10 I minus 15 root 2 over 2. So we'll just we'll put the I on the outside.
Professor, for the velocity B, isn't the cosine and sine supposed to be switched? In the I direction, would it be sine 45?
If you're going this way, so that's 45 degrees, right? So that's cosine, right?
I guess it's going to be the same either way, because I was looking at the other angle. And if it was the other angle, it'd be, or the 45 angle that you drew originally.
Yeah, I mean, you're right. I just
same,
used this one, but you're right. If it was, you'd have to use the complement. Otherwise, you'd have to swap them. But you're correct. It's just the fun of having 45 degrees, gives you more options. Okay, so then we're going to do that, and then we're going to say 17.32 minus 15 times the square root of 2 over 2. And so we end up with essentially a negative 20.6 I plus 6.71 J. And so we can then find the magnitude, and it turns out to be 21.7 at an angle of 18 degrees roughly, if we take the square root it and then use the tangent to find the angle. And so that tells us 18 degrees. And so if we go back to this, we could then draw it like this. Right? Because of our equation, we know that VA relative to B, we know that that's going to be VB plus VA relative to B. So tip to tail is going to be 2 tips, so that's VA. So that's what, and if we take the 18 degrees, the 18 degrees is really here. That's the 18 degrees, right, squeezed into that little part with relative to the horizontal. Now you can see that with this, because we know these angles internal, we could have used the law of sines and cosines to find it too. We could have said that the law of cosines would have said the velocity of A relative to B squared equals 20 squared plus 15 squared minus 2 times 20 times 15 cosine of the internal angle, 75. So that would have worked also. And we're actually going to do that for the part B. So we found VA relative to B, but now we want to find the time when they're 800 feet apart. So to do that, we redraw, given what we know, our diagram. And so I'm going to draw it again like, oops, wow, that was good. So what I've done is I've redrawn it, and I know this is 75 degrees, and I want to know when this is 800 feet apart. That's really what it's asking. it wants to, because you have the two boats, they're going in opposite, not completely opposite, but they're diverging. So when is the distance from this to this 800 feet? And so how do we figure that out? Well, we know this is a distance, but we know that this is traveling at 15 times time, and this is traveling at 20 times time. And so what were original, we were given, our units were feet per second, right? So we can then figure out, based on the law of cosines, what the time will be just by plugging in. Okay, so what we'll do is we'll say, we know, and you should have the law of cosines and sines. If you don't know them by heart, you should have them written down in your notes. So remember that for that rule, it says for a triangle that looks like this, if that's A, B, C, and this is A, B, and C, then it essentially says A squared equals B squared plus C squared minus 2BC times cosine of little angle A. So we're going to do that here. We're going to say 800 squared equals 20t squared plus 15t squared minus 2 times 20t times 15t cosine, and we're going to have space, erase that, of 75 degrees. Okay, so what we end up with is just some simplification of all this. We end up with 640,000 equals 469.7 t squared. And so t ends up being 36.9 seconds. Okay. So now we solve for the time it took them to get apart. Any questions on that?
Since we took the relative velocity, like in that direction, wouldn't we just be able to multiply or divide 800 feet by that velocity we just found?
Would that work? I don't know. What is 800 divided by 21.7? I would try it that way. It seems like it.
It does come out to 36.9.
Does it? Oh, good. Well, that's a good alternative. But this way I got to use my law of cosine, so I feel better about it now. But yes, that's in by all means, if you guys find, other ways to solve the problems, by all means use them. I'm not saying that my way is the only way to do it. Okay. Any other questions on this? All right. Okay, so let's look at this example. Now, as I mentioned, I was going to do an example with relative motion and projectile motion. Let's find the piece of paper I drew for this. Where'd you go? Here we are. Okay, so let's go ahead and look at this problem. So here it is on the screen. So you have the ball, the boy throws it in the air, and when he throws it in the air, it has an initial velocity the same as the deck in the x direction. But the difference is, once he throws it in the ball, and we're neglecting air resistance, it's going to maintain its initial x velocity, whereas the deck itself is actually going to slow down. And so because the deck is slowing down, the ball isn't going to land vertical again right where the boy is. And so the boy is actually going to lag behind the ball because the deck's not moving as quickly as the ball is anymore because it's slowing down. So he's going to have to step forward a distance d in order to catch it. So we know the height, 8 meters. And so knowing the height, 8 meters, we know that if we calculate the initial velocity, that's also going to be the final velocity. So when it goes up, it comes down again. Again, neglecting air resistance. All right, so there's a few steps in this problem, so let's go through it. So here we have the drawing, and so we have our deck. We know that the ball is going to go up and down, height of 8 meters, velocity of the deck's that way, acceleration of the deck is that way. Now, so let's first look at the ball. And so for the ball, the horizontal motion, so x horizontal motion, we know that the Vx is going to equal Vx naught, meaning that whatever the velocity in the x isn't going to change. It's going to stay the same. And therefore, the distance the ball moves is just going to be equal to whatever that initial velocity is in the x times the time. And so we don't know the time, but we're going to find the time because we know, because it's a projectile problem, we know that if the ball's thrown up and falls down, we can figure out how long it's in the air. So now we're going to look at the vertical motion of the ball, or in the y direction. So we know at that one, we know velocity in the y is just equal to initial velocity minus gravity times time. We also know that Vy is going to be equal to 0 at the peak. So we know that once the ball hits its peak or its apogee, it stops moving. We know that the distance of the ball, y of the ball, is equal to y naught plus velocity. And maybe I don't really need the b in there because that's what we're talking about is the ball. So just say y equals y naught plus vt, and then minus 1/2 gt squared. And so we're going to hold on to this equation, but we also know that we can also write Vy squared minus Vy naught squared equals -2gy. And so these are basically our 3 kinematic equations that you guys have been using all through physics. Now, because we know this equation actually comes in handy because we know that sorry about that. Turn that off. Because we know that we know the height, we know gravity, and we know that the ball is 0 at its peak, then we can really we know that's 0. And so really the negatives cancel. And so what we end up with is the velocity of y initial is equal to the square root of 2 times 9.8 times the height, 8 meters. And that might look familiar from your so we end up with initial velocity in the y is 12.53 meters per second. Okay. Now, one thing to consider is if the ball starts at not initial velocity in the y at 12.53, then its final velocity in the y is also going to be 12.3. So V final at impact, or when it's caught, equals 12.53 also. So this will come in later. All right. Now, so let's think about how long is that ball going to be in the air? Okay. So we know that because we know the initial velocity and we know the height, then we can now figure out what the time is. And so we go back to our equation y equals wait, let me check something here. Oh yeah, y naught and then that's going to be plus v naught t minus 1/2 gt squared, right? So then we're just using our equation. So if we plug in, we know that this is 8 meters, and that's 0, and we know that's 12.53 times t, and that's minus 1/2 9.8 meters per second squared, and then that's times t squared. Okay, so what we've done is we've created a quadratic equation, and now we can solve, and we can get t is 2.55 seconds. Okay, now because we know it's 2.55 seconds, and we know that's how long it took, then we can use that to calculate our x distance. Now, so let's go ahead and do the next step now. So now we're looking at the motion of the deck. Now, remember that in terms of this equation, let's go ahead and cross out line and then go. And so what I would say is that we're going to have to go to another sheet, but remember this value, 12.53 meters per second, and this time, because we're going to need those later. So have those in front of you. When we look at the x, because we're trying to find the velocity of b relative to d, so in the x direction, we're finding the, remember what we're going to do is we're trying to find v b relative to d, but we have to do it for both the x and the y direction. So b relative to d in the x direction, we know is just equal to the velocity of the ball minus the velocity of the deck. Okay, now we know that the velocity, like I said before, the velocity of the ball is just equal to vx naught, the initial velocity in the x direction. And we know that the velocity of the deck is going to equal vx naught, and then that's going to be plus acceleration of the deck times time, because remember the deck is slowing down. The ball isn't, but the deck is. So we have to add this into it. So if we come over here and we write VB relative to D, notice that VB minus VD, if we do that, we get VX naught minus Vx naught plus acceleration of the deck times t. And so effectively these cancel, and we get VB relative to D equals a negative, and then that's times a negative because the acceleration is going to the left, 0.3 meters per second squared, and then that's times our time, which is 2.55 seconds. And so our VB relative to D, and that's in the x direction, is going to give us a value of 0.766 meters per second. All right. So we need the total B with respect to D. And so remember that what I said earlier was that the ball, what goes up comes down. And so if we think about the ball when it's coming down, the ball with respect to the deck is the ball's falling kind of like this, where this is its straight down velocity, which is the 12.53. And then this velocity here, which is its x velocity, which was 0.766. So you can either write this as VB relative to D is equal to 0.766 I minus 12.53 J meters per second, or you can write it as 12.55 because that's the magnitude when you square root them. And then that's going to be at an angle of, this ends up being around 86.5 degrees. So that's this angle here. Okay, so that would be the proper way to present it. Any questions so far? Okay, good. So the only other thing we have to figure out then is what is the distance. So we want to know what is that distance that the ball goes, or the boy has to walk in order to catch the ball. So we know with that x, b relative to d, and that's what we're looking for here. That's that distance that the boy has to with respect to the deck. And that's going to equal, because he's walking on the deck, so that's why we say with respect to the deck. It's not an absolute distance like if we were to take a point, say, on the shore. So xb minus xd, right? Now we know that the distance xb, or the distance the ball moves, that's just equal to v naught, the initial velocity of the ball, times time, right? Because that doesn't change, there's no deceleration. And we know that x of the deck is equal to v naught, initial velocity of the deck, times time, but minus 1/2 acceleration of the deck times t squared, as the deck slowing down. And so here you have the same thing we did in the past problem, is because we're subtracting these two, we're basically going to subtract that and that, and so those are going to disappear. So what we end up with is xb relative to d equals initial velocity times time minus initial velocity times time minus 1/2 acceleration of the deck, t squared, or essentially just equal to 1/2 acceleration of the deck, t squared, which we know is 1/2 0.3 meters per second squared times the time squared, which was 2.55 seconds squared. And that gives us a nice 0.979 meters. All right.
I have a question.
Yes.
Is the 2.55 seconds the time it takes to get to the apogee? Wouldn't you need to multiply it by 2 to get the full distance?
No, because when I use this equation back here, this one actually it was, yeah, this was, so it starts at 0. It's a cent. Yeah, when I found it in here, it's how high it goes, and then no wait, I'm sorry, this gave me the initial velocity, and then this gave me the time that it takes to get back. So I'm trying to think if I put 16 in there or not. I see what your point is, because you're right, the way this is set up, it almost looks like it's a 2.55. I don't believe so. And let me look back on my original notes. I don't believe I put 16 in for that. I solved it. Let's see. Yeah, I'd have to go back and check. So I'm not sure, but it does account for that, but I can't remember if I put in 16 or if I did something different. But you're right, it does. You have to account for the fact that it goes up and it goes down.
Okay, thank you.
Anything else on this? Okay, good. All right, so I did post the second homework assignment online, and it's available. It has it's missing a couple of problems, which I'll post tomorrow, and those are from chapter 12. So there's just a few final problems in this for chapter 11 that deal with polar coordinates and radial. And so what I want to do is go over the theory of that real quick, and then just to present you with where those came from. And then we'll do some examples on Wednesday. And then we'll also do polar coordinates on Wednesday. And then we'll meet, of course, live on Friday and start jumping into chapter 12 where things get more interesting. All right, so so the end of chapter 11 deals with non-rectangular components or tangential and normal components in polar coordinates. So I know you guys are familiar with those from your time in calculus. You've used them in multiple. And so I know that polar coordinates can get pretty messy. And so we're gonna use those at a limited basis. But as long as some of you are more abstract thinkers than others, and I think that can be a challenge in this class, is because sometimes you just have to check. If you're an abstract thinker, that's good. If you think more of like real terms, that can make it a little more challenging, because a lot of times you just have to trust the math. And I'm not saying that you can't visualize. It's just that sometimes it's hard to visualize. And so the math works, but then why does it work? And that's something you just kind of have to work out on your own and I'll do my best to kind of explain it, but everyone learns in a different manner. So if we look at you may recall tangential normal components. Anytime you have a particle moving along a line that's not straight, then you're going to have a acceleration towards the center of that radius of curvature in the normal direction. And so we break our velocity up into two components. One is the tangential velocity, and that's a vector that's just equal to the scalar velocity times the unit vector. And then we also have the normal vector. And the normal vector then is always obviously perpendicular to our velocity. And so there is no normal velocity, but there's a normal acceleration. And so we relate that by the equation A equals dv dt times et plus v squared over rho times the unit vector and the normal. So the acceleration is two components. It's just the time derivative of the velocity times the tangential unit vector, and then it's the velocity squared over the radius of curvature times the unit vector for the normal direction. So these things right here in the upper, this is probably the most important part of this slide, or just these equations. Now, in the subsequent equation, it talks about how they're derived, since I've had questions about where do these come from. And so this is just essentially walking you through the derivation process to give you the two equations that we just had. And this is in your book, and I provided it here. It's not something I would test you on, but it's certainly something that's interesting if you want to know where the equations came from. You also have and this goes on, and you can see that the final result is the tangential acceleration is dv dt, and the normal acceleration is just v squared over rho. And so you can see that because you can break them apart, that there might be problems where you'll have to do integration in order to solve for it. Lastly, we have this third vector, and that vector comes from the fact that if you take the cross product of the tangential and normal unit vectors, you get what is called this binormal vector. And in our class, we won't have any acceleration in the binormal direction, but you can imagine that it is possible to have that depending on the particle's motion. And so that certainly makes things a little more complicated for the math. And so if you take intermediate dynamics, which I know some mechanical engineers have to, or if you want to take it just for fun, then you will be doing stuff where you actually deal with that binormal plane and the binormal vector. Actually, the plane's called the osculating plane. I'm not sure where that came from, but it's a good 50-cent word you can throw out to impress your friends, of course. Okay, so that then is where the equations come from. And we haven't even got to polar coordinates. We'll get to those on Wednesday. But this conceptual question says if you have a race car around a track at constant speed, at which point will the car have maximum acceleration? So if you look at the racetrack, we know that acceleration is only if it's a constant speed in the tangential direction, then the only acceleration we have, so dv/dt is essentially 0, is our acceleration in the normal direction. And so that will only occur, or that will occur where the radius of curvature is the smallest. And that would be part A. So when we look at something that's moving along a curve, and we have something like this, then if you think about a curve that goes, say, like that, then as long as you're, say, right here, then you're going to have that acceleration towards the raised curvature. But as you hit maybe right here, which would be an inflection point, then your acceleration normal goes to 0. And so an inflection point is really where the line is straight. So if you're driving down a straight line, then we know the acceleration normal is v squared over rho. But if rho equals infinity, then this essentially equals 0. Okay. So that's where I'd like to end today. I've given you a lot to think about, but on Wednesday, we'll go ahead and we will pick up this and we'll talk about more on polar coordinates. So the slide set I just showed you is on Canvas, but it's going to be changed and updated with more slides. So be sure to re-download it before that meeting. Otherwise, I'll see you guys in office hours on Wednesday. If you have any questions, remember homework's due tonight at 11, and the new assignment is posted. So thank you guys. I look forward to seeing you for real on Friday. Have a good week.
Thank you, Professor.
Thank you.
Thank you, Professor.
You're welcome.